a number of honorable judges, Leonid and Idan from Nebius. Thank you for the sponsorship and for judging. Congratulations to everyone who made it to the end of an arduous journey. Shipping CUDA projects is non-trivial, as I'm sure many of you discovered today. But I heard a few success stories, and so let's see you all appeal. Demos will be 6 minutes long in their core. And my request with demos is that you go into as much technical depth about the alpha or whatever it is that differentiates your project as you can. It should be an intense learning experience for everyone. Every demo
should or should not?
It should. You should come away from every demo knowing something that you did not already know, understanding how to implement something you didn't already know how to implement. One of the upsides to having everyone share GitHub code is that it's possible to explore so much code in a really short period of time. So it's a deep experience. We'll be competing for glory in third, second, and first place. So do appeal well. The judges are watching. And with that, let's hear it for Ash, Vardanian, and Sasha on CUDA Accelerated Shoals Voting.
Thank you very much. Okay, guys, so I will remind you what the project was about, even though I mentioned it briefly in the morning. So there's this algorithm called the Schulze voting method that all the pirate parties use. It's a really good algorithm. We could have titled the project Scaling Piracy, but we decided to go with Scaling Democracy because it also makes a lot of sense for like democratic elections. And when you look through the notes of this algorithm, a description of this algorithm on Wikipedia, you see that it's like 3 nested for loops. So it looks very similar to matrix multiplication. Matrix multiplications work fine on GPUs. Maybe we can find a way to remove the sequential dependency from the algorithm that looks like matrix multiplication, but is not entirely matrix multiplication, and make it run on GPUs fast. And I kind of started prototyping this in the last couple of days, and I had like a baseline in the morning, but the democracy we had in the morning was a flawed democracy. The algorithm was wrong. What we did with Sasha today, we kind of deflawed the democracy, and we also scaled it further. So we accelerated the algorithm by another 50%. The way we got there is through a few iterative procedures. So first, when you look into the algorithm, unlike conventional tiled matrix multiplication on GPUs, it's a multi-phase procedure. So we cannot just independently process every tile of the matrix C that we want to compute as a product of A and B. We have to split it into tiles, and then some of the tiles have to be processed in a very specific order. First you go through the diagonals, then you go through the horizontal bands, the vertical bands, and then in some specific order you process the remaining tiles independent from each other. In every one of those traversals, the procedure, again, is kind of somewhat different from matrix multiplications. In most of them, you would see 3 shared buffers, which have practically level 2 caches on the GPU. So 3 sub-matrices, A, B, and C. But instead of just invoking one kernel or just fetching one scholar per thread, you actually do multiple passes in a somewhat weird ordering. But the hardest part for us was actually finding a way to skip some cells within every tile. So the diagonal elements within tiles or interleaving enumeration order has to be avoided in some very weird way. Luckily, because we could use C++17 instead of older versions of C++ CUDA dialect, we could use if const expert. So the kernels that we had were super short with mostly compile time constants on the top for both tile size, synchronization, and diagonal checks. There's also a trick that is somewhat neat but completely useless in this case. Maybe it would come as a surprise to you, but oftentimes CPUs introduce branches even when you have a logical or bitwise operation. They would replace it with logical. So instead we do arithmetical operations where we could have done bitwise operations. And all of those improvements, they kind of compounded one on top of the other. In the morning, an algorithm with a mistake in it worked and kind of took like 3.5 seconds. And Sasha right here will talk about how fast it works now.
Yes, so here are some Google charts I generated just before this presentation. But yeah, so as you can see, we have the size of the input here. So this is like the number of voters.
Number of candidates.
Number of candidates that people are voting for. So if we have a very vibrant democracy, we might have 32,000 candidates trying to be president. But unfortunately, our CPU would just break and take like forever. Like it couldn't finish 16,000 candidates. But yeah, so as you can see, this is all log scale. But the GPU is just orders of magnitude faster than the CPU. And then, as you can see here, actually, our throughput is still going up, which means that the GPU should be able to handle much bigger problems without breaking its sweat. Like, we're not really maxing out the GPU. So this means that both we have some more room for optimize our implementation, and it means our democracy could potentially grow to 128K levels of vibrancy.
We kind of also estimated the efficiency of this algorithm. So it's one thing to be fast, another thing also to be efficient. And we noticed that we're like probably about 3.5 times at this scale more energy efficient than the CPU implementation. But also like the TTPs of GPUs are much higher, so we can squeeze more throughput from a single chip. So the cool aspect of this is systems like this can empower like direct democracies and direct elections, where you have like thousands of choices and you rank them partially, but then through combinatorial optimization procedure, all of them are being organized in somewhat fair order. I'll make sure to write an article about the limitations of this voting system as well, so that we're kind of fair to other approaches, such as majority voting. But that's kind of our project in a nutshell. Thank you all. Any questions?
So the particular traversal you were talking about is specific to this algorithm, or is that you're talking about this like going down the diagonal and then?
So
that's the peculiarity of the Schultz voting algorithm. Or?
In like the short answer, probably yes. The long answer, no. So if you like familiarize yourself with like, let's say, a few hundred of combinatorial problems, and like if you're into this space, you'll notice that a very similar procedure happens in a lot of places. It's somewhat different, it's somewhat application specific, but once you do it like a few times, you kind of get a grasp of it and you realize that there's so much more space for applications of parallel hardware architectures than originally thought. So I would definitely recommend going through the code base and maybe trying similar approaches somewhere else.
Is there like a search term you would recommend for that?
Oh,
like a search term to learn about this procedure?
I will write down an article tomorrow probably, like that will be a few thousand words most likely on similar topics. So we'll make sure to publish it somewhere. Yeah.
On Nebius AI you will publish it here. If
Oh, happy to.
If you're happy with it.
Sure.
Right.
I'm curious about the, you're saying it's kind of like a matmul and kind of not.
Yes.
How far do you think you can push that paradigm, where you're able to?
Oh, very far. So there is this thing called algebraic graph theory, which is one of the unexplored kinds of graph theory. There's also like conventional dynamic programming, there's spectral graph theory, and algebraic is my favorite. And if you like dive into the space deeper, you'll realize that like half of the combinatorial problems can be re-implemented in terms of matrix multiplications or similar operations. And I spent like a few years working on those. So maybe like a good reason to open source one more library.
I would just like to mention though that a lot of this stuff works very cleanly because we use like a dense representation, like an adjacency matrix. If you were to use an adjacency list, you would probably need to use some sort of sparse matrix multiplication tricks.
Yeah,
yeah,
that's very fair. And you would probably avoid implementing kernels directly in CUDA. Sometimes it might be like tricky. That's one of those places where thrust and comp are very handy first entry points, like when you start working with really sparse representations.
So do the intrinsics still give you a lot of value, or are you kind of having to freewheel it in terms of implementing?
a specific case, intrinsics gave us literally nothing because, so we didn't use warp level intrinsics for synchronization because the problem was data parallel within a tile, and we couldn't use any SIMD intrinsics in CUDA because SIMD intrinsics in CUDA are for 1 byte or 2 byte values. The smallest values that we have in this problem are 4 byte values, which is identical to the size of the word in CUDA. So no SIMD this time, sorry. Any other technical, non-technical questions? Yeah?
Did you guys, so I don't know if this fits for your algorithm, did
Yeah.
you consider using DPX instructions?
Yes, DPS is also like 1 byte, 2 byte, or like relevant for 1 byte and 2 byte values. This is 4 bytes and bigger. Like DPS is like special kind of NVIDIA SIMD, I would say. Yeah, but amazing instruction, one of my favorite. Okay, anyone else? Well, thank you all. Make sure to check it out and contribute. Thank you.
Yeah, congrats on the speed up and the real implementation.
I mean, it's a win for all of humanity.
Maybe we all vote with speed and confidence. Travis Cline is going to give us CUDA Live, a real-time torch.compile renderer. Let's hear it for Travis.
All right, so as Jeremy said, I'm going to share what I called CUDA Live. Perhaps it should be called Triton Live, but we'll get there. I also have to just note that I did not directly only offer CUDA code here, and so I'm at risk of being shouted off stage. We'll see if I get kicked out for this. Okay, so what did I write? This is inspired by the CUDA mode Discord community and YouTube series, which is basically like, let's all like get together and get better and better at CUDA. One of the languages in the CUDA ecosystem, I'm sure a lot of you know this already, is Triton, originally a project from OpenAI. It's gotten lots of contribution. What I wrote here is basically a view into the output that Torch Compile produces, which basically is a static analyzer that optimizes your model. It does that a lot of ways. One way I think is interesting and that I focused on here is that it generates Triton kernels from your vanilla Python code. So just as a small demonstration, the resolution here is not what it should be. Okay, so just as a demonstration that this is actually working, and if demo gods play along, so like as you edit the code on the left, this has like a WebSocket connection to a backend service with an H100 connected to it, and talks to Torch Compile, and here will live render like the change to the Triton kernel associated with it. Of course, this is a very, very simple program. It's literally like calling sign in a row. This is almost as trivial program, mapmul in a row, but if I throw in like some scalar multiplication here, sorry, that's tiny. You'll see that multiplication is automatically represented here. So the idea here is just like a tool where you can just type code and really quickly, without scrounging through a bunch of temp directories, understand what is the Torch compiled Triton kernel associated with your work. And I will note for the cases where, so here I'm running scale.product attention here. That's not just one single Triton kernel. In that case, I don't just show the Triton code, but I show like the entire compiled model code, which does have like multiple kernels present here. In that case, the generated call here is often very, very interesting. So this is still very, very early. I think there's some interesting places to take this, like actually run these things and show relative benchmark numbers. Was chatting with Nico, who hacks on PyTorch, about some ways like maybe CUDA events or profiling output could be introduced in here. So some cool places we could probably take it, and it's open source. I'm TMC on GitHub, so it's TMC/CUDA Live. So please contribute to it and help me hack on it if you like. Any questions?
Should put it on Compiler Explorer.
Okay.
What is compiler explorer?
Godball.org?
Yeah.
Yeah.
What is that?
You feed it source code and it spits out the assembly. So it's exactly what
Oh,
you're
sick.
doing, would fit super well in that.
Very cool. Very cool. Yeah, obviously this is just like showing the kind of direct torch compile output, but going like an extra layer and getting closer to like what's actually being sent to the accelerator, I think would be very interesting. Any other questions? Cool. Thank you.
Okay. Jared, Hulbert, let's hear about kernel and kernel.
Yes.
Uploading our kernel work to the GPU.
So this is kind of background here. So the idea here was to, as I talked about earlier, to try to see what we can get inside. There's things you do inside of an operating system that you end up doing as like these large arrays of data, and you're accessing, basically you have a struct, and you want to pull a count out of the struct is the simplest case that I'm actually modeling. And in an operating system, there's a lot of reasons why you want to do this as a, maybe there's some atomics, maybe you've got different things you're trying to test for and check for. So you want to kind of do it in a nice simple array. A lot of uses, however, just need the big blast of data, right? And one of the things that's happening is, if you think about an operating system, what's it for? It's for allocating resources. And as the resources have expanded, you're seeing that you got a lot more metadata. So you're getting to the point where these arrays are kind of large. And so you can spend a lot of time in a single thread kind of incrementing through this stuff. So the hypothesis is pretty straightforward. What if we parallelize it, right? Well, the question would be, well, what about the transfer? What about some of these things? So the big question I wanted to answer is would it be worth, in a very simple case, would it be worth doing this in CUDA and transferring stuff to a GPU to speed up kind of what the kernel does? So I can kind of show you here. Shoot. So if I do this with just in C, we see it'll take about 2 seconds of, or in this case 1 second. Why is it taking 1 second now? So it's about half the time to do it on the GPU. Now, what's interesting is this is an H100, so obviously, you know, it's a kind of a little bit overkill for this, but it actually wasn't super impressed with the size of the GPU. I think, you know, there was kind of maybe a limit to the scaling, that the speed of actually doing the calculations was pretty trivial compared to the cost of kind of migrating. One of the things that we found was when we actually tried this out in the beginning, the CUDA version was about half the speed, or then we got it kind of about the same. And what we found was I was trusting kind of the compiler and the system to do the managed memory under CUDA and to get that right, and it was a lot slower. So the big fix was, you know, our code is pretty straightforward. Where am I? We didn't do much. It's kind of ugly, but the main kernel is just a very simple, I kind of pipe in this array of structs and I reduce it down from a struct into an array of longs basically. And by doing actually doing an explicit mem copy, setting it up as device memory and then copying from the host, it sped it up by about 3x. So I'm kind of surprised, to be honest. A lot of times versus the managed memory. I should have had that implementation. I might resurrect that and put that alongside it in the repo. But I was kind of surprised that the compiler and the runtime didn't figure out what I was trying to do better. I started to try to do some mem advise. I don't know if anyone's got a lot of experience doing mem advise stuff. I was hoping maybe that would maybe give it some hints, but I didn't. I was having a problem getting that working for some reason.
So we're comparing traversals of unified memory versus just like pure device memory. And you also tried doing like mem advice with unified memory.
I started that. I never got any results.
Okay, yeah. That sounds realistic. Like mem advice is
touchy.
Yeah. It's like prefetch on the CPU practically.
It was just I didn't know what the stupid numbers I was supposed to type into the advice was and stuff like that. So pretty straightforward. But next steps. I want to kind of go beyond this and start looking at two things. One is that this probably isn't worth it, but there's more complex versions. This was the simplest case I could think of in terms of kernel work that does this. There's ones that are a lot more complex. It's like, okay, well, I got a ton of things in this array, and then I want to, resize them and apply some masks and so forth, and then create a new data set. But they're all kind of these reduce type work that I'm doing, right? Take a larger array and reduce it down to a smaller array. So I want to start looking at those and play with intrinsics, and then if I can kind of convince myself it's worth it, I'm going to think about, okay, how do I actually implement this in the real world? So, yeah. Any questions? Yeah.
Do you think it'd be worthwhile to also try this on like an integrated GPU, like if you have this
absolutely.
GPU?
Yeah. I honestly, I think you try to do this in Mac, it's probably way better, right? Because you don't have that GPU to whatever. Man, I am really tired. That transfer is, I think, killing us.
And then my second question was, CUDA depends heavily on like the user space driver, at least on Linux, right? Would you have to implement a lot of the user space driver to get this working inside of the kernel to get it working?
I'm not 100% sure the right direction for that. I'm pretty confident that you can get a binary that you could do some loading for that, right? You have access to the driver in the kernel, obviously. But yeah, that is one of the big questions I would have is like, what's the right way to do this? Like, can I even do it in CUDA? Yeah, probably not. I probably need to go straight to PTX. But neat thing is, once you kind of peel this away, the intrinsics are pretty simple, right? And like you're already in the freaking kernel, so transferring memory is going to be arguably a lot simpler to do that. Now there are some intermediate things that I might do in my practice, because my startup does this kind of work where I'm using AI to speed up and enhance the kernel. So I might, as an intermediate step, extract the data raw, right? Do it in CUDA and then use it. So I don't know yet.
Okay, cool.
Any other questions? All right, thank you.
That was kernel and kernel. Next up we have Rohan, who's trying to optimize some group GEMM in Cutlass. It's here for Rohan.
I guess just to get a benchmark here, who here is familiar with the distinction between batched gem and grouped gem in CUDA? Okay, sweet. So I can like say a lot of bullshit and no one will know.
The video never lies. This video exists forever.
Yeah, I mean, not bullshit, but just like I'm definitely I learned about this stuff today, right? So I mean, I will mess up for sure. People on YouTube who are watching eventually, please forgive me. Okay, so I guess I'll start with like talking about like what GEMM is. GEMM is just like when you're doing a matrix multiply on a GPU. You want to do these like batched GEMMs when you're doing a bunch of these matrix multiplies at the same time, and they're of the same shape. So normally when we're like running these traditional LLMs like Llama 7B, whatever, Mistral, Small, etc., everything is fine. Everything is like the same shape. Everything is nice, and you can use the batch GEMM operations to run those because everything is the same dimensionality. But once you switch to like a mixture of expert setting, you now have different numbers of tokens going to different experts. And what this means is that now your matrix multipliers are no longer the same dimensionality. You can't run the same, you can't use batch GEMM operations because they assume that all your matmuls are going to have the same dimension size. So instead what you need to do is use these grouped GEMM operations. And those have, those are a lot more complicated because you need to handle all these kinds of edge cases for handling all of these like differences in dimension size and so on. So there's a lot of problems with like group GEMM now that MOE is like coming more into common usage. People are running into all kinds of errors with these group GEMM operations in Cutlass with like on the backward pass when there's like some ratio of expert workload, like something breaks. Another guy reports like group GEMM, yeah. So like specifically in the case where you have below 64 examples in your batch during inference, like you only have 20. Then you like run into these issues where you can't use group GEMM operations because they use the TMA, and that has like a multiple, like you need to have at least 128 elements there. All these kinds of like really weird things. So I was talking to Pradeep from NVIDIA this morning, trying to find out like stuff to work on, and yeah, he suggested just like going down this like group GEMM rabbit hole and like optimizing stuff. I think what ended up taking most of my time is like just getting Cutlass to build. And actually just like getting to start playing around with this stuff. But I was able to like on the Nebius H100s, I was able to get Cutlass built and like start running some benchmarks. So yeah, I mean everything. Yeah, I mean you can see like the builds over here and like running benchmarks. You can see all these like the runtime it takes for running all these group GEMM operations and so on. I guess I'll run one of these like my version of a live demo. Yeah, look at all those. So that's nice. In terms of actually doing these optimizations and fixes, I only really started going down like specific kind of optimization directions like an hour ago. So still working on that, but there's a lot of interesting stuff here. I definitely learned a lot. This was definitely an interesting hackathon. So yeah, thanks guys. Yeah, I don't know if it even makes sense to ask questions, cause like, but like, yeah, I mean, if you want to know about group GEMM operations.
So we're
Oh, we definitely have questions.
Yeah.
Oh, really? Okay, go ahead.
So you probably use the MMA intrinsics, right?
Yes. So I mean, the group GEMM operations all use MMA right now. Well, so here's the thing. So batch GEMM uses WGMMA in Kublas. In Cutlass, it seems to me from the code that they both just use MMA. But theoretically, there's huge performance gains to be gained from like switching to WGMMA or something like that in Cutlass. But none of the Cutlass code, as far as I can tell, uses WGMMA anywhere.
Well, what's the tile size for FP8 that you use on H100s?
I have no idea. It's probably somewhere in one of these files.
Oh, so like it's buried in the abstractions, and you assemble the existing abstractions around FP8 kernels for group matrix multiplication, right?
Yeah, I think this is all of these are. I assume these are FP8. I assume, yeah, all the benchmarks are running FP8. I think so.
Okay. And one more question, like there's like 2 flavors of FP8, I guess, that are supported in H100s, like the E4, M3, and...
I have no idea.
Okay.
Yeah, I mean, this specific benchmark, yeah, I mean, it doesn't have specifics on what it just says it's for Hopper architecture. So either it's like buried in some abstraction for like the FP8 stuff is under the hood.
Okay.
Yeah, something like that.
Thank
Yeah.
You mentioned that this is a particular problem for MOE
Yeah.
models. Why? I'm not sure I follow that.
Yeah, so when you're running an MOE, you're sending different numbers of tokens to different experts. So that basically means that like one expert, you'll need to do like 30 matmoles of the same dimensionality, and then another expert, you'll have like 10 matmoles, right?
But you're operating them in parallel, essentially.
Yes, exactly. So that's what this group GEMM stuff is for, essentially.
When it comes to ease of onboarding, I guess Cutlass build seems like a pain point.
Yeah, it
What
was
your
kind
build
of.
pain, and like how do you think the CUDA environment could improve the experience
Yeah.
of a first-time user?
Yeah, I don't know. I think for like the seasoned CUDA professional, I'm sure it's like trivial. But I think there is a lot of work to do. There's increasing interest in CUDA hackathons or like CUDA projects. Like this is our first like CUDA hackathon, and like there's a lot of people here who shipped interesting code. I wonder what directions are meaningful for like lowering barrier to entry for people writing kernels. Like
I
meta.
was asking you.
Oh yeah, I guess I sort of just mirrored that question back to you. Maybe some kind of like, honestly, stuff like what Travis did in terms of like visualizers of like, yeah, like this is what your PyTorch compiles to in terms of Triton. That direction seems useful. Maybe some form of like web like simulated environment where you can like play around with kernels without having to like go and like rent an H100 and like test things there.
Yeah,
But like it's probably very non-trivial to like simulate. Yeah. Yeah.
Was there any handholding that could have gotten you over with spending all your time with Kubas building?
I was yeah, maybe some handholding, and I did get some handholding for sure. Like not like sitting next to me, but I went and asked Pradeep like questions plenty of times.
Nice.
But yeah, thanks guys.
Okay, that was GEMM in Kubas. Up is Jeremy with ML Lightning, CUDA accelerated machine learning,
Where's Jared?
which is great. So I'm just going to crash. Okay. Welcome to ML Lightning, CUDA accelerated classical ML algorithms. I'm Chairman. I guess I have this existing library called Oracle. And Oracle is a library built about 9 years ago. It basically is filled with algorithms, like bagged decision trees, canon regressors, canon classifiers. I'll show you a few examples. It's really typically, oh, I can't see this, sorry. You guys can see it, sorry. Okay. This is Oracle. It has sort of simple Python implementations of, for example, k-nearest neighbors classifiers, which basically, initialize a model, use NumPy arrays to basically like fit and predict. In the case of k-nearest neighbors, it's almost entirely inference, where you're just doing lookups of nearest neighbors and sort of aggregating counts at runtime, and then it'll like pull in some specific data source and just run it as a simple example. This was basically made for educational purposes, so for the intent of understanding how every algorithm worked. This is a much more complex implementation of a convolutional neural network, which defines a dense layer, comp2D, uses M to call and call the M to efficiently compute the forward convolution, and which has gradient computations and basically a prep delta computation for computing the deltas that aren't before were the layers that have parameters happen to be defines activations, and then has like a way to set the topology and does the backward pass with, in this case, Adam. For the ML algo examples, both simple and complex, I set up basic CUDA implementations in what I'm calling ML Lite, machine learning library. And the intention is really the same as Oracle. So similar body of algorithms, except these are all relatively simple CUDA kernels for each major algorithm. And I guess I'll run you through an example. In the case of convolution, I have this Python setup. It's this dense matrix representation. In the case of the CUDA kernel for the corresponding algorithm, we initialize a number of relevant values. So as you can see at the end of the convnet, we do import MNIST and train the model on MNIST. And so similar story for this sort of CUDA convolutional setup. It's basically going to be on MNIST, so we have some initial values that we'll be using. There's an in-to-call kernel, which is much more sort of like lengthy and definition heavy, but you can kind of see the side-by-side of my original like NumPy implementation of image to call and the image to call implementation in this CUDA kernel. So I guess, if you don't know, basically convolution, you can sort of slide over the image, and that's a relatively slow way to implement convolution, is just to look at what the transformation is as you move the kernel over an image. But you can also do some simple matrix operations in order to automatically basically make all of the transformations happen with a single big multiplication. And so m2call basically sets up a unique matrix which has in various positions all of the appropriate convolutional kernel and underlying image overlaps. And then that is the matrix that you do a big multiplication with in order to basically immediately compute all of the convolutions over a given image in a really fast way. So for a lot of these, for m2call and call to im, so in the backward pass, you have to invert this m2call matrix operation. And so this is the Python and CUDA implementation of call to im. Let me grab it real quick. Sorry, for some reason I'm not big. Oh, I like run.t on like image to call. But this implements the inverse operation, the call to im kernel. Similar story to forward pass. So Python on the left with this sort of like iterated sequence of for loops that's moving over the channel count, it's moving over the weights. Very similar story, on the CUDA side, iterating over the channels based on the filter size and making sure that everything's in the appropriate place. ReLU is implemented, dense forward, etc., softmax. And a similar story, it ended up being like a very lengthy implementation. But at the end of the day, we end up allocating memory to all of these different like filters and ReLUs, etc., and has a training loop running for this basic convolutional neural net. So I did struggle getting all of this to run. So like this code basically was set up as the first pass attempt at replicating the totality of my Python implementation in CUDA. And so I don't have a side-by-side on runtime, unfortunately. But I do have basically like a big first step in the direction of creating all of the relevant CUDA implementations of all of my library algorithms. So welcome to ML Learning. Any questions?
What would you say was the hardest part for you in like switching your mental model from Python to CUDA in this?
The memory allocation was a big mental model. Yeah. I actually haven't dealt with it since I was like sort of playing with C++. So I made a C++ version of this library as a creative project like 5 years ago. Actually, even then, I don't think I explicitly did that much memory allocation. So yeah, it really was a pretty big throw to have to like manually free and allocate all of my memory. Kind of obvious, but
just as a comment, I think like once you start optimizing this and looking at like kernel level, there will be like so many interesting places like where your mindset would change. Like let's say, when I see a division by integer or like a modular operation in a CUDA kernel,
Yeah.
like I almost have like a panic attack.
Oh no.
It's like,
So I wrote very Python.
it's like super expensive.
I would say
And then like, let's say if you do a for loop, there's like so many ways how you can, let's say, tile some of those operations. It's like on the GPU, everything you do is built around the mindset of like you're reusing CPU caches. So it's like one step further.
I see.
like-
Yeah. We should probably sit down and you should just tell me all of the ways in which this is totally
like-
egregiously Pythonic CUDA. And I believe you. I'm sure. That's
I think like once I give like 3-hour talk on how just like to do reductions differently
Yeah.
on one model of a GPU. So like at the level of an entire convolutional neural network,
Yeah.
there's like so many like millions of places where things can go differently.
Can we just get like an hour of Ash roasting Jeremy's code and just like record it? I feel like that'd be super valuable actually.
Any other questions? A request for an hour long.
So, what do you think about the layer of abstraction, like the level of abstraction at which you'd implement this into CUDA? Like from because it's like largely from like a pedagogical type of purpose, right? So like, does it make sense to like still do the thing where you have a high level Python kind of implementation that then calls to CUDA kernels and you write really clean, simple kernels for doing convolutions and stuff? Or like why did you decide not to do that and to instead do it? Like, let me just straight up port the entire thing in the CUDA vibes.
So the primary value of this for me was like learning. So I was just like, okay, let's go side by side and let's keep everything simple. So I just wanted to run. I actually really value the abstraction diffs.
Okay.
I'll like take care of that later is the intention.
Sure.
I'm sure that that's faster than what I'm doing. But also, I guess I'm like somewhat interested in Mojo or some setup where I don't have to constantly be calling back and forth between CUDA and Python or between CUDA and C++, and where I can just implement a simple algorithm and it can function. So yeah, a part of me wants to do Mojo Hackathon where like the default way in which I implement these things is actually very Python.
There's also Numba, right, which is like Python.
It's merged. Yeah, merged representation. Very cool. Thank you. Okay. Wian Stipp. CUDA game of life. On deck is Riya. With fast long.
Alright, thanks.
Let's hear it for Wian.
Alright, so does everyone know what the game of life is? I'll give a quick example just so you get a sense of what it is. So it's this ecosystem with some basic rules. So it's a matrix, and then there's some replication rules. So you know, if there's a cell with fewer than 2 neighbors that are alive, then it dies, and yeah, some other rules. So if you run this, it produces some interesting patterns. So yeah, what I decided to do is I realized this has some parallelism kind of embedded in it. So yeah, decided to implement that. Firstly, just to kind of POC it, I started with Python. So yeah, I didn't spend much time on the rendering aspect of this, the terminal, but you can kind of see it's doing stuff. And now I'll give Ash some more heart attacks. First, I went to C. This is my first CUDA program, by the way. So, but yeah, first I went to C and implemented it there, and then looked for opportunities to make some things more parallel. So it's very basic. The main kind of body function is this update next state. It's just doing this basic logic. If for the point you're looking at, if there's less than 2 live neighbors or more than 3 live neighbors.
Can you zoom in on that code?
Oh yeah, for sure. I also don't write C code, so then the next state for this one gets set to 0 and so on. So yeah, this is the C version, and then finally this is now the CUDA version. And I went through a couple of steps here. So I was thinking of doing something with
firstly putting it in a 32 by 32 block, because that all fits in one CUDA block, I think. And then, maybe using some of the shared memory. I realize that doesn't actually really help me very much, but the implementation that I ended up going with is using one block and then a grid of 32 by 32. And then the main, this is that parallelism now, so just grabbing the x and y coordinates and then calling this count neighbors function to then, I think this is probably the part that's not very good. So this is, within the kernel, it's calling this function to then grab the sum of neighbors around it. This is the part, I think, that can probably be optimized more. But in any case, I was also figuring out, and this is, stuff to look at next, how, what's the best way to not just, run this on device and then iterate, because, at some point you actually want to look at the results in the terminal or copy it back to CPU. So, I don't know if this makes sense, this CUDA mem copy async, but this allows you to actually render it whilst you're running on device. It seems to work, and the results are the same as the C code, which is good. And then finally, I was benchmarking this. So if you do 100,000 steps, in Python it's around 62 seconds, C it's 2.5, CUDA 1.78 seconds. And then if you don't want to look at the intermediate results and you just want to kind of get to an end state, then it's 0.88 seconds. And I'm sure this can get much better. But this is, for 32 by 32 grid. I think if you want to run it on a bigger grid, you could probably do something smart with using blocks and then kind of overlapping them to compute locally the next cell states and then aggregating and continuing like that. But that's it for now. And kind of the motivation behind this is I was brainstorming, maybe there's a way, if you guys have heard of the ARC AGI challenge, maybe taking this, generating data, and then pre-training a model on some of that data, having an agent embedded in the game of life to take actions and so on. Maybe you learn some good primitive patterns that are useful for reasoning and to help with this challenge. But yeah, that's it. Any questions?
What's an agent in the game of life?
So game of life is typically a 0-player thing, but I guess you could actually embed an agent in it, like something that's able to modify the game state. Let's say to maximize the number of life squares, or to make a thing to destruct something else. Things like this.
That's cool.
But yeah. Yep.
So I'm sorry. So where where did the speed up come from with the C to the? Maybe I missed something there.
So
did you do much parallelization?
Yeah. So the parallelization was so you've got this block of 32, let's say, and then for each of those cells in parallel, you want to count the neighboring ones. So what I was doing is I was spinning up a thread
For each one.
and then rather than looping over on CPU. Yeah. Cool.
Make your tiles sparse by storing tuple addresses and then write a kernel to operate over that.
Yeah, that's a good idea. There's a ton of sparsification optimization. Yeah. Yeah, good idea.
You actually started talking about that. Game of Life in some sense has like locality because you have this, spacecraft, you have to update it locally with, in your example, grid of 32 by 32.
Yeah.
But like in some time it's going to move, and somewhere there where you could have computed something in parallel,
Right.
now you have to take into account that spacecraft that moved.
Right.
Are you following me?
Yeah.
Right now? Okay, cool. So, did you, as you were, you started talking about it, do you have any intuitions of how would you implement that? You said overlapping grids or something else.
Yeah. No, I didn't think about it that deep, but that's a good thought. All right. Cool.
Yeah, thanks.
Riya, Dhruv, Andre, and Ken. Let's hear about Fast Llama. custom kernels to speed up Llama 3. Wolfram physics is on deck.
Where the Llama guys?
Fight.
Okay, so our project is Fast Llama. So a bit of an overview is we wanted to enhance the performance of Llama 3 by implementing custom kernels, and we specifically focused on RMS norm, which is the normalization step in the model, and then we did some benchmark to measure the time difference between the base version versus our custom implementation, and yeah.
So the main idea with like the custom kernel, we picked RMS norm because we figured that's what's used the most, and we used PyTorch profiler to benchmark. And so our first run of benchmarks was that sort of base PyTorch eager, we generated like 256 tokens. It was like 11.7 seconds, then that went down to 2.2, which is suspicious. These are screenshots. So this was like our first run, and so this is CUDA time. Resolution isn't that great, but if you have good eyesight, this is 11 point something seconds. This was our first run with our new optimized kernel, which showed like I think this is like 2.2 seconds, and this was suspicious. So we ran our own kernel again, and once again got the same 2.2 seconds. So we went back and ran the first initial eager model, and turns out that was now 2.15 seconds. So yeah, there was something up with this first run. But total time was still brought down. There was lower CPU time with like our custom kernel.
Yeah, so I'm just gonna explain a bit about like the RMS norm CUDA optimization. So this is just like the profiler plot where it shows the tensor library like dispatches that PyTorch eager will give you, and in our case we only dispatch like the RMS norm kernel. PyTorch eager by default uses a bunch of other things to achieve the same logic. And in terms of the CUDA timing there, it's like roughly a 50 microsecond difference, which is, I guess, pretty significant when we're talking about 100 microseconds. And yeah, just to kind of talk about at like a high level some of the optimizations that we did. So firstly, we looked at like cooperative groups, which kind of allows for more granular barrier synchronization and warp specialization with like warp synchronous programming techniques. And we kind of looked at like, okay, since RMS norm is kind of like a two-loop function where you go through the batches and go through the sequence length and then apply some linear, some constant time operations, we said, okay, why don't we reduce over one dimension and over the other, and then we kind of like came up with a warp reduction scheme, and then later do a more general like block reduction scheme. We also did some like stuff with cache streaming intrinsics like LDCS and STCS, so making use of interesting cache hints, which at compile time it will say, okay, is this expected to be used much, if not substituted out, or keep like the very used components. Also some parts of like constant memory as well to make use of that 64K like buffer for the user space. And yeah, I mean, there were also some things like for the constants looked at static const expr versus const expr and like the performance difference between that. Not to say that that was a very big improvement, but it's like something to look at the machine code and say, okay, well, you know, this is like producing this versus this. And yeah, I mean, from this, the naive implementation of the CUDA kernel saw like roughly 1 order of magnitude speed up. This one's probably like 5 orders of magnitude speed up compared to the CPU implementation, which is pretty nice. And yeah, this was like kind of the core of what we swapped out in the Llama model and ran benchmarks with. Yeah.
Yeah. So one other thing that we also explored is if you look at the architecture of Llama, rotary positioning embeddings are applied at every single layer. So we thought that that would also be a good area to optimize. Unfortunately, we ran out of time, so we were unable to integrate it. But the performance of the kernel itself, I think is pretty good. We see an almost 10 times speed up, around 8 to 9 times, between the CPU execution time and the CUDA execution time. So a really good next step for this project would be the integration of this kernel and perhaps even optimizing it even further with double buffering.
So the baseline was also on the GPU, and there are new kernels on GPU now, right?
Yeah.
How much of the runtime on the GPU was the RMS norm initially?
Well, I mean, when we looked at the actual profile chart, it doesn't really say. It kind of groups up a lot of them together, but you can infer kind of how much based on the number of dispatches over there. It says around like 50 dispatches for the RMS norm kernel that we implemented, and then all the other stuff on the default implementation of the model with no substitution. They dispatched like, I don't know, 4 or 5 different kernels that achieve the same thing with roughly the same amount of dispatches per. So you can probably extrapolate that to like 5 times more, I would say, maybe 4 to 5 times more.
Is it like 5% of the forward pass? Or
Oh, yeah, probably even less than that actually, just because of like the timing overall. Like we only really saw 300 millisecond speed up on like the proper test, which is, if my math is right, probably around like, yeah, 3 to 4%, which is, you know, not bad for start. Yeah.
Congratulations. Awesome speed up. All right. Wolfram physics with GPUs is up. Let's hear about trying to optimize the Wolfram models. Let's hear it for Lev and friends.
Alright, so yeah, our idea was CUDA meets Wolfram. And first, I will talk a little bit about the Wolfram physics project itself. And the idea behind it is that discrete structures can generate very complex behaviors, even the very simple ones, much like the game of life we've seen earlier. And so maybe if you take a hypergraph, which is a generalization of a graph, apply some rules to it, then at some point we will get something like this. And there's a bunch of different things there. It's much more complicated, but that is the basic idea. And the algorithm, which everything depends on, is taking some hypergraph, which differs from a graph in that one edge can consist not of not 2 vertices, but any amount. And so it represents it like this. And we need to, and the rule is represented as a hypergraph substitution. So we need to find some sub-hypergraph and replace it with another hypergraph. And so if you think about a little bit about how to implement it, you will realize that this scales very badly. And so you can apply the rules in different places of the hypergraph, especially if it's large. And then parallelization is really useful. So basically we took a look at the, we can generate beautiful structures like this. First we took a look at the official implementation of the hypergraph substitution model, and we profiled it. We took at which we took a look at which functions take the most time to complete, and first we just took one of them and just implemented some CPU optimizations, and that got us already a 20% reduction, at least in the tests that we were using, that 20% speed up. But then it is parallelized on CPU, but still doesn't utilize the GPU at all. And so then we started taking a look into how we could offload some of the work on the GPU. And so there are a couple of papers on how to do subgraph matching on GPUs. And so we started integrating those into the official implementation. However, we didn't have enough time, so we didn't do it yet. But imagine that, so currently we have a 20% speed up on CPUs, but we imagine that probably if we finish integrating the algorithm so basically when we are looking for subgraphs, we are adding one by one the candidates for the vertices, for the tokens of the graph to the rule input. And so there's a lot of branches happening there, and the idea behind the algorithm is that you parallelize the branches. And so we didn't implement the subgraph pattern matching yet, but that is the goal.
So I tried working on this at the first hardcore hackathon. The thing that I was really struggled with was like graph representations. And I finally found, I meant to show you the code that I had worked on. I finally found it. The thing that I struggled with was like actually the graph representations and representing the graph in a way in the GPU such that you can perform like mutations anywhere in the graph without having to do a ton of shifts, right? Because once you like let's say you have a vector like this, if you realize you have to mutate somewhere here, your pattern matches over here, then now you have to do this read from here, create more space, and then write over here, right?
But you don't really need to mutate on the GPU. From the profiling, the overwhelming majority of time I spent on the actual pattern matching, because once you have matched it, then you just need to swap stuff, and that's pretty fast compared to finding the big combinations of different edges. Like there's a lot of different options that you have to brute force through, basically. And so that's the most basic part.
So you're working from the Wolfram implementation. Okay, cool.
Yeah,
well, I guess
that is the main part, the isomorphism of subgraphs.
Yeah, I see.
What's the ratio of computation time?
It was 80% because like it was a recursive function like at the start, so like there's a lot of stuff that we would be able to optimize them.
In your case, Rohan, there's like a way for you to filter out parts of the like in their case it's hypergraph, but if they put like an upper bound on the rank of the hypergraph, they can represent it as like a low rank tensor, let's say tensor rank 4 or 5. Yeah, and then for small subgraph isomorphism problems, they can do like enough like permutations of those within like a small tensor and a GPU.
Yeah,
that
if you start doing like sparse matrix. So.
Yeah.
Yeah, I guess that's what I was like also sort of curious. Like, what do you think now? Like having profiled the Wolfram implementation of all this stuff, would you consider like would it be faster to go and write from scratch like a CUDA implementation of this stuff versus going through and fixing like the Wolfram implementation?
Good question.
I don't believe so.
I think if you either way you have to implement the isomorphism.
Yeah.
And so that's what the time depends on. And if you want to reduce the time, I think you can reduce the time a lot by transferring this onto the GPU. And so then it basically doesn't matter whether you write it from scratch or you use the implementation, because that's the function that you're going to have to rewrite anyway, and the time depends on that function.
All other visuals are good enough actually. So like you basically just need to implement this bottleneck function on the GPU, as I understand.
Yeah.
And they were using, like in the paper, they were using the graph structure as a vector of edges, and then a vector which shows which edges belong to which node. So like just two vectors, and like this was enough for them. They had a lot of micro optimizations.
I wonder if you could do lookup, like do this kind of search that you say is bottlenecked with some like generalized form of a convolution that you run over. Like if you represent it as a matrix, right? You can like convolve over the entire matrix representation of the graph and then extract wherever it's like highly activated. Something like this.
I think that would constrain you to some only some rules. For instance, for those that have the same area of all the edges, like the same number of vertices in one edge, or something like that.
Did you guys start from Maxim Peskunov's equivalent? Yeah.
Isn't there a problem because like we don't have a lot of locality like in our hypergraph, so we wouldn't be able to use like the cross of locality in convolutions?
Well, yeah. You could also, so for some constraint rules, you could probably, so if the rule generates some space-like structure, which it should do if it aims to represent the universe, then you can do a lot more parallelization because you know that something that is like here isn't going to be connected to something that's here, and then you can offload that to different kernels.
Very interesting. Release the game of life.
Yeah.
Very cool.
Yes, correct. Are you going to submit your 20% CPU improvement back to the set replace repo?
Yeah, sure.
Nice for it. Okay. With that, we have the image upscaler using CUDA by Lily Sue. Let's hear it for Lily.
I'm just presenting a pretty simple, like getting started kind of project. This was like my first time working on working with CUDA and setting that up on my laptop as well. So basically what I did was I'm just taking an image that I found online, an image that pretty much looks like this. It's my like nature like JPEG. And then I have this CUDA code that upscales this image. So I'm just gonna run it now. What it's doing is that it's loading the image and then it's initializing like OpenGL, so GLFW to preview the image. And then like it creates like the GLFW creates the image for display. And then it allocates memory on the GPU and copies the input image data. The reason why I picked the image upscaling as the function for my CUDA project is because every single pixel is running on its own thread. It's like a massive like parallelization, and it copies the result. Like once the processing is done, it copies the result back to the CPU memory and then saves it as a PNG file and frees up the like resources. So my processing is done, and I'm just going to show that the image has been upscaled. It's going to take a second because the image is kind of large. So I chose the Lanczos filter in terms of its efficiency because it's
So this is the upscaled image. Basically what I did just to prove that it's upscaled is I upscaled it just by the width and not by the height, like 10 times. And I chose this particular filter because it's better performance than bilinear interpolation. And what it does is that it's a continuous function that like balances like smoothing of sharp edges, but still avoids aliasing artifacts. And it's known to be more effective at preserving high frequency details over rapid changes. It gives less pronounced oscillations near sharp transitions. And basically the mathematics behind it is that it's taking the sync x, like x being the pixel, times the sync x, the pixel divided by a, the a being like around 2, like negative 2 to 3, to positive 2 to 3, and it's pretty much normalizing around this particular continuous function, or like computing 0 otherwise. And basically what it generally looks like, instead of just maybe like a round spherical kind of degree of transition, is that it's a little bit more like a upwards hill, like that, but it's going from 0 to 1. And what else? Let's see. So in terms of the running on GPU aspect, is that each pixel is computed independently. It's like a floating point calculation, and there's 16 threads in each dimension of the image, and 256 threads per block. And so basically, for each image, either it's the width or the height. It's like adding by 16 minus 1 divided by 16 is how it's computing how many blocks it's going to be computed over the image. That's pretty much it.
Do you have another implementation of Access that's in Python or C++ or another non-CUDA language to know how much of an improvement you got by using the GPU CUDA?
Yeah, that's something I should try, because yeah, that like it will be a good comparison to see the difference.
Can you show the code? Is it?
It's on my
Let's get
GitHub.
the
It's pretty good.
Yeah, it's just a kernel that CUDA. Okay. Last but not least, Stereo OMG. Real-time 4K to 3D video conversion. Real time.
Is that doubt? Just hear some doubt?
Oh no, I was hoping to be impressed.
Awesome. Hi everyone, we are Stereo OMG, and we're going to be talking about our real-time 2D to 3D 4K video conversion. Okay, great. So let's talk about the underlying technology first. So the kind of 3D video we're doing is essentially stereo vision. So this has been a technology that's been around for a very long time. When you are filming a scene, you use 2 cameras, and then from that you can extract some locations within that scene. So you can imagine that there's real application of this in all of these self-driving cars. So a lot of this data that's collected uses 2 cameras. The problem is that most videos that we have aren't collected like this with stereo vision. And people in computer vision are well aware of that. What we're trying to do is apply this to essentially any kind of video, maybe for like consumer use or just somebody wanting to do this in a project. So how do you take some video that isn't collected with stereo vision and then go get this mapping? Well, there was a model recently released called Depth Anything. They train on over 62 million labeled examples of this kind of depth vision. They have this kind of like LiDAR data mixed with multiple cameras. Essentially, they just released this model that can just take any kind of arbitrary video and create this depth mapping. And so our goal was to take this and package it into something that could run real time, for example, on an Apple Vision Pro, taking any video that's collected and then turning it into something that's 3D. Okay, so we're essentially using this model as a black box. So it can take any video scene. In this case, we're using Star Wars. You run it through this labeling model. It runs really quickly. The optimization's already there, so it runs over 100 frames per second. And then it creates these depth frames. And so you have a side-by-side between the original video and this depth mapping.
So the problem is that there's nothing to turn this into a side-by-side video, because ordinarily you have to collect the side-by-side first to get the depth map, so no one ever bothered to create a depth map to side-by-side. A very naive implementation using a couple for loops in Python is like a quarter of a frame per second. It's really, really bad. So this was just the worst implementation possible of a for loop over the frames, the height, and the x. And then I tried vectorizing this with NumPy as much as I could, and still it goes from a quarter of a frame per second to like roughly 10 depending on the hardware, but it's still not high enough to be real time. So this is what we did.
So we have a kernel here that's doing some pointer math on our frames to take our depth map and our picture data and remap those frames based on the depth map so that we can generate our stereo vision from a single frame plus the depth map. It's relatively short kernel, but the speed up is incredible over the Python code. I mean, this one runs so slow that you don't even have a single pixel there. It's the 0.25 frames a second that we mentioned before. We got up to 115 frames a second on 4K video. So this is well past real time. You know, Star Wars was 28 frames a second. So this could be pipelined and run in real time in a video player to convert 2D video into 3D stereoscopic video. Yeah.
Yeah, so I have a non-pipeline version, but this is kind of just like what it would look like. Let me do the screen share in a second. Whoa. Okay. Cool. Is that working? Awesome. So can you guys see the video in front of me? So this is the side-by-side video, and essentially I'm just going to take the, thank you, and I can just switch that to left to right, and then now I'm watching Star Wars, and you can see that I have the entire couple hours, but the idea is to kind of be able to do this in real time, and then maybe even, you know, watch YouTube videos, all of them in 3D. This has been hard to share because it's really fun to do copyrighted content, and yeah, that's the demo.
It's also not stereoscopic up here, so.
Yeah, it is in 3D. But
just take his word for it.
That's the idea behind showing the side by side before the 3D is it renders it as 3D on your there's two screens, so you have the left and the right image. Yeah. Yeah. There's our team.
Can you guys show the kernel?
Yeah. So it's just a horizontal offset on the frame data.
So did you guys like stream Star Wars to the server and like turn it into this?
So we uploaded some files and just did it in place. This is not yet pipelined, but with NVDEC and doing demuxing, we could pipeline it. Right now we're just using OpenCV.
Yeah, FFmpeg libraries are not fun to compile in C, and especially also using like NVIDIA's H.264 decoding, getting that all together in 5 hours, and this. I didn't even know C++ since yesterday, so we thought it was a good starter.
So we had like the DSP intrinsics mentioned today, I think this is like one of the places where it makes sense. So you see like the min-max line 11 and 12. Seems like the perfect place to avoid like 2 branches, and you're precisely working like on a board, 32-bit board of 4 8-bit integers.
Totally.
Can be another optimization place, but
for sure.
nicely done.
Did you pick the 4K like size just because that is like the best, or is it that it most clearly delineates like Python from NumPy?
So
like it crosses the gap between real-time and non-real-time.
So the question is why 4K?
Yeah.
Because I was like sick and bored in New Jersey a couple months ago, and this sounded fun. I just have a bunch of really high quality rips on my media server, so it was just what I had, and I was just
even with the performance we were seeing, though, 1080p wouldn't be up to real time with the Python implementation.
Oh, yeah.
Oh, it's cool. What was the NumPy 1080p frames per second?
Do you have a measure on that?
No.
I don't know if we haven't measured, but like quarter frame a second is like.
Well, this was with looping, right? Not vectorization. Vectorization got you like a 40x speed up.
That's fair.
Yeah.
Well, I imagine if you want to do like a naive comparison, like 4K is roughly like how many, like what factor more pixels than 1080p? 4. Okay, so yeah, 40
So
frames
from
per second.
1080 to 40 FPS, and like for a good experience in goggles, you probably aim for 120 FPS,
Well,
or like 90 plus.
Like the movie's not going to go any higher than what it was filmed at.
Okay.
It's a 28 FPS source.
Oh, okay.
So yeah. The thing is, you can actually, like, depth anything has so many parameters to play with. Like that 100, over 100, it's like, there's kind of a trade-off between how high quality you want the depth map and how fast. And it is a massive slider that you can do on that. You could get it running hundreds of frames per second if you didn't want a high quality depth map. That 100 is like based on really quite high quality depth map information. But yeah, play around with it.
Going stereo is one thing, but probably like adding intra frames for a good experience in VR can be like another hackathon project. That might be cool.
It's a good idea.
Is that like what NVIDIA does? Or are you talking like adding the in-between frames?
Yeah.
Yeah, I think NVIDIA does that right on the device to give you like extra frames or extra pixels.
Yeah,
Games.
they do super resolution as well. So like they do a lot of stuff now around games.
Yeah.
Cool. Any more questions for stereo? And congrats.
Whose laptop is this?
That's mine. Can you just grab it?
I guess we can also mention, while everyone is still here, that there is a QR code here on the laptop from Nebios.
Oh.
So you can all get like a $200 extra on your account if you want to play with H100s a bit more next few days.
Yeah, battery just.
Oh, amazing timing on my behalf.
Yes, you're right, timing. I will share once again on Slack.
There is actually a link on Slack, so if
Yeah.
you're on Slack, you can already like just follow up there.
Okay. So we have a special final presentation.
Oh, one more.
Yeah. Silence! So it's a very special week. This week it's Rohan's birthday. So I was thinking it'd be amazing if the Hardcore CUDA Hackathon sang Rohan a warm happy birthday. So 3, 2, 1!
Happy birthday to you. Happy birthday to you. Happy birthday.